This will be the only day I lecture in this room. I don't like lecturing in this room. It's not set up for lectures. Normally I'll give the lectures on Monday in the Story building up the street. And then we're just going to, when we're down here, we're just going to be working the lab, and then the TAs and I will be here to help you with your designs. So we'll just be walking around answering questions pretty much. So we'll have one lecture per week. The reason I'm lecturing today and here is because we missed Monday's lecture because the semester didn't start till Tuesday. Okay, so let's just go through the syllabus here real quick, and then we'll get started. We have the catalog description here. This class is basically about CAD tools and hardware description language. This class has two sections. Both sections will be together on Monday in lecture, and then half of the class will be in the lab here on Wednesday, and the other half will be here on Friday, and that's obviously because we don't have enough room in this lab for the full 60-student section. You can come in here anytime you want. The combination is on there. It's 45213. I am going to use Blackboard because they're forcing us to, but I record my lectures and I put them online in case you miss a class or you want to hear it again. Or if you go on there on my YouTube page there, you can see every lecture I've given since 2018. We're going to be using CAD software that's installed in this lab and I believe in 1D43 too, although I think pretty much everyone comes to this lab. You can install the CAD tools on your personal machine if you want, and we can help you out to do that. It's kind of a pain. You have to download like a 70 gigabyte file, but it can be done. The only thing that you won't have on your personal machine are the FPGA boards. So we're using these boards. They're the same ones used in 313. And so you'll be testing your design on these boards, but you can simulate them using the CAD tools. So you can do a lot of the work without the boards. The boards are just to basically check to see if your design, if the behavior of design in simulation matches that on the actual hardware, which it doesn't always do. Because simulation is kind of ideal, and and the boards are real hardware. Make sure you check your email for course announcements. So whenever I need to get a message out, I'll post it on Blackboard, and then I believe it automatically emails everyone at their email.sc.edu email address. So make sure you're on top of that, because every once in a while we have a change in a due date or something like that. And we will have teams in this course for the design work, but the department doesn't offer any way to collaborate between two people. So you'll have to figure that out on your own. Okay? So if you save your design on one of the team members' accounts, then you might want to have a GitHub repo or Dropbox or something like that to share data. And then if you have any issues with the lab, you have to contact Ryan Austin, and I have his email address there, because I don't have any administrative rights in the lab, because they don't trust me with that, even though I was administering Linux machines when Ryan was in diapers. But they don't trust me to have root access, because I might delete everything. We have a textbook. If you go to the next page, so there's two versions of the textbook. They're shown on the second page. The one on the left is the MIPS edition, and the one on the right is the RISC-V edition. We used to use MIPS in this class, and a few years ago we switched to RISC-V because it was kind of the more trendy thing to do. Both textbooks are very similar, and they're both very good. They cover VHDL and Verilog, or System Verilog, kind of side by side, so you get to see both languages. They have different syntaxes, but the semantics of both languages are the same. It's just the syntax is much different. And they also have a lot of hints about how to design the CPU. So if you can get a copy of either one of those, it's great. The RISC-V edition is the better one. Okay, Section 5 has the course learning outcomes. That's just for ABET purposes. Section 6 has important dates. So we have a cancellation, as always, for Labor Day on September 1st. So we'll have a lecture on Monday, and then the following lecture is canceled. I also have, let's see, we have fall break. We have a cancellation for fall break, but it's just the labs. And then right after fall break on October 13th, I have a travel day, which unfortunately is a Monday. So I think we'll cancel that one unless Alex is going to be willing to give a lecture.
I can do that if you need me to.
So what's that?
I can do it if you need me to.
Yeah, we might do that depending on where we're at. Let's see, and then Thanksgiving we have a whole week off, so we'll miss lecture and lab. And then the final exam will be on December 8th. Now the final exam is a little weird because this is kind of a non-standard class. We have the two sections, and it's kind of one section is Monday, Wednesday, the other one is Monday, Friday. So I chose the Monday, Wednesday final exam day. Hopefully there's no conflicts. There usually isn't, but if there's any issues with, of course you guys are in the Monday, Wednesday section, so it doesn't apply to you anyway. Okay, section 7 has the instructors and teaching assistants. I have office hours this semester, Tuesday, Wednesday, Thursday from 11 to 1. Just to make it simple, I chose the same times. I'm also available by appointment, and my lab is up in the Story building across from Strom Thurmond. And I just moved offices. I went to the other side of the building, so note the room change is 2263. I am now on the east side of the building instead of the west side. We have two teaching assistants, Soyash, Soyash, are you here? No, Soyash is not here, but Alex is. So Soyash is, he's based out of my lab in Story 2236, and Alex, you can have a desk in the lab. We don't have you set up. Alex is a new grad student, so Alex may be eventually based out of the lab as well. But I just have their office hours by appointment. So the idea is that you can get a lot of help from the TAs and me when you come to lab. If you need help outside of lab, then you can schedule a time with the TAs, or you can come to my office hours. Okay? So we have plenty of opportunities to get help. Section 8 is the grading structure. There is a graduate and honors version of this class that involves a 5th project that the regular version doesn't. And so as a result of that, I have to apply different weights to the graduate and the undergraduate version. Section 9 is the schedule. So we have 4 labs. Labs are projects, basically. 2 are easy and 2 are hard. The first 2 are just basically 2 weeks. And then the 3rd and the 4th are longer. You can see on the schedule there. Hopefully we can stick to that schedule. The labs do build on one another though, so you have to complete them in order. Okay, next page. Disability support. If you need support for extra time on exams, contact that office. The contact information is there. Section 11 is the syllabus change policy. We don't typically change that, but just to let you know, if we make any changes, we'll give you notice. Section 12 is the grading scale, which is just standard boilerplate. Section 13 is the academic honesty policy. So in this class, we're using CAD tools that are hard to use, historically. They're not user-friendly. I usually joke that the CAD tools, you kind of get the impression when you're using them that they were designed by like high school interns. Like the user interface is terrible. And they haven't improved in the 4 or 5 decades they've been developing them. I encourage you when you're in the lab that if you have issues with the tools, like they're crashing or you're getting unexpected behavior, to help each other out. That's one of the advantages of being in a lab, especially if like the TAs are busy. You'll notice that in some cases you might have to wait for help for a little while because sometimes it takes a while to solve problems in the lab. However, we don't want you to share code or designs, obviously. Please don't do that. So help each other with the tools, but not with the solutions to the labs, to the design problems that you're working on. Okay, 14 just says that lab attendance is optional. However, so the lectures are, as I mentioned, I post the lectures online, so you can watch those online if you miss a lecture. And I have all my old lectures online too. The lab, we have 2 labs allocated for the first project, 2 labs allocated for the second project. And by labs, I mean, the 75 minutes that we have in the room reserved for. And then the third project, I think we have 3 labs reserved. And for the final project, I have 6. But it may take you longer. You shouldn't expect that you'll be able to finish everything in just the amount of time allocated in this room for each project. So just keep that in mind. Okay, next page is group work policy. So we ideally will work in groups of 2. That's just based on hardware availability, although you should be able to work in a team by the time you graduate. Make sure you choose your partner in your group wisely, because the lab grades are the same for both members of the group. However, we do have a large, as you can see in the grading structure, there's a large component of your grade is individual. That's the quizzes and the exams. So if you have a lab partner that doesn't pull their weight, it's still kind of works out in the end, right? Whoever does the work in the lab is going to tend to do better on the exams and quizzes. Okay? Any questions about that? Yes. Yes. Yeah. There's a few classes. I think the only other class, I'll have to get a schedule of what other classes are in here. I think 313 might be taught in here, but I think that might be the only class, right? Robotics used to be in here, but they now have their own lab. So, but I'll have to get that from Austin, what the schedule is.
So for testing quizzes, is it like on paper, or is it like just...
The quizzes will be online. I give those on Blackboard. And those are just basically for practice. And the exams will be in lecture, in the lecture room. So those will be given, no, they'll be, yeah, writing little snippets of code and that kind of stuff, solving. Yeah. Yep. Yeah. I mean, I used to give them online, but in this era, with ChatGPT, we got to go. We got to switch back to the old 17th century method of paper and pencil. Yes.
I know the mixing is on here, but like the quizzes and like other things.
The quizzes are pretty much once a week. Or once every 2 weeks. I think I have 7 or 8 quizzes in total over the 15-week semester. And the exam, the midterm, I have that scheduled on here. It's October 20th, and then the final is December 8th. So they're both.
So all all these I have the names of the names of the group. On the second section.
Which section are you?
On 9.
9? Oh, those are top. Well, yeah, kind of. Yeah, pretty much. Those are the topics, and there's pretty much like 1 quiz per topic. So that's about right. Yeah. Yeah, I'm going to start out talking about RISC-V. So this class requires you to know assembly language. I'll talk more about that a little bit later. And students in this class always say, yeah, we learned assembly language in 212, but that was 2 years ago, and I forgot it all. So I'm going to give you a refresher. We'll go over that again to refresh your memory. And then we'll go over System Verilog, which is a language, a programming language. So you just learn a new programming language. And then we'll talk about microarchitecture, which is something that you also covered a little bit in 212. Except in this class, we're covering it more from an applied perspective. So I'm going to give you kind of a recipe on how to build a CPU and actually build it in reality, in real life, out of logic gates, or out of System Verilog, which is synthesized logic gates. So, and then once we get through that, we'll have some conceptual topics on timing analysis, building blocks, and then by the end, I even get into CMOS logic design a little bit, because we don't have a VLSI design course. We don't have a design for manufacturing course, like how you draw mask layers to build an actual chip. So I'll get into that a little bit at the end, just to give you some conceptual material on that. So the first 2/3 of the course are kind of applied, kind of, technical school style. Here's a language, here's how the CPU works, let's build it. It's meant to be hands-on. And then the last third of the course is it's from the textbook, and it's just concepts, more of a traditional course. But as I'm covering that, you'll be kind of finishing up your CPU in parallel to that. Does that make sense? Okay. Any other questions? All right. I think that's it for the syllabus, right? Oh, yes. A couple other. Sure. Yes.
Is the extra graduate project, is that a video thing as well, or is that something individual?
Well, that's always kind of tricky. So typically, there'll be a grad student and an undergrad in the same group, and then only the grad student does the project. If you're in a group with another grad student, then you can both work on the same project, that's fine. But that's kind of a logistical thing. But I don't mind if you work on a team on the grad project. It's not always possible. Yes?
This class applies to the accelerated masters, are you considered a grad student?
Yes, it does. Yeah, honors, accelerated program, or grad credit. Okay, and that's a university policy, but that's not me just being a dick. That's required. You have to do an extra project to get graduate credit. Okay, let's see. So projects are real hard to grade, it turns out, because we're building a CPU, and in real life, basically there's no partial credit. You either deliver a CPU that works or you don't. Like the customer just wants it to work, pretty much, right? Likewise, it's kind of hard to grade. It's really tough to grade these projects. I've been teaching this course for almost 30 years now, I guess. 1999, I guess. And never really figured out a great way to grade. We've tried, project reports. I had a student one time that worked really hard on creating a machine grading system, like an automated system that it would run your design through test vectors and just kind of take the design through its paces automatically. But if you were off by one clock cycle, it would give you a 0, like blow up. So we've never figured out a great way to do it. Generally, the way we've been doing it is over the last few years, is demos. So we just have you demonstrate your project. So the way that works is the project will have a due date. You have to submit it on Blackboard by the due date to get full credit. But then you can demo it at any time after that. You won't get a grade until you demo it, but you won't be penalized if, for example, you demo it after the due date, as long as you have it submitted by the due date, right? Now, we're assuming that whatever you demo is whatever you submitted. So, and if that turns out not to be the case, that would be considered cheating. Because we generally demo in class while we're also answering questions, sometimes the demos kind of get pushed back a little bit, but we don't want you to sweat that. You'll submit it on Dropbox, and that'll timestamp it, okay, for when you submit it. That make sense? So submitted projects, they have to compile both the hardware and the software to receive partial credit. Only one group member needs to submit each project, which is kind of a pain for us to work that out because, we have to make sure that we know the team members, all the team members, so we can track that. So next week I'll be asking you to email me whoever you choose as your teammate, okay? But only one member needs to submit it on Blackboard. As I mentioned, the project is assigned in part or whole based on a project demo, and both group members have to be present for the demo because we'll ask you questions just to make sure you understand how your design works. Projects are due by 11:59 on the due date. Now, if you're late, that's okay. We have a very generous late policy. So each school day that it's late is a 5% penalty, but it's capped at 30. So even if you submit, bless you, even if you submit your projects like on the last day of the semester, they'll only receive a 30% penalty. Of course, then you have to demo them somehow, which would make that difficult. But we have it capped. The reason we do that is because, as I mentioned, the projects build on one another. So if you start to fall behind, it's very often the case that someone will fall behind on a project, and that sort of backs you up on on subsequent projects. So that's why we have this late policy. Okay. Now you can only submit one version of each project. This always comes up every semester. Someone submits one and then they want to submit an updated one. No, just one. Just submit one. Because we don't want, because otherwise it'd be easy to game that late penalty system. Any projects not submitted by 11:59 p.m. on Friday, December 5th will receive a 0. So that's the cutoff date. It's the last day of the semester. Okay, any questions? Good. All right, so I'm going to go ahead and get started. So what is this class about? This builds on 211 and 212. And I know it's been a couple years since you've had those classes. Unfortunately, we don't have a very good, the sequencing is not ideal. So what was 211? You guys remember? That was digital logic design, logic gates and such, right? Digital Boolean logic, breadboards, that kind of stuff. And 212 was really about two main things. 212 is supposed to be, about half of 212 is supposed to be assembly language, and the other half is like CPU design. And then you might also cover things like arithmetic and floating point and that kind of stuff. But mainly 212 is about assembly language and kind of how data paths are established inside of a processor, a microarchitecture. Okay, and then we want to take that knowledge and use it to use modern CAD tools and modern, semi-modern now technology, the FPGAs, to build a working CPU from scratch, which is pretty cool because a lot of times, like you might remember from 313, you use these FPGA boards, but you use someone else's CPU design, the NEOS, right? NEOS processor is a MIPS-5 processor, and I think they have a RISC-V version of NEOS now. But you treated it like IP, intellectual property, where you kind of just built your design like with Legos, like with building blocks. In this class, everything that goes on the FPGA will be put in there by you. So you'll design everything from scratch from the bottom up, as opposed to from the top down. Okay. Okay. So let's see. In 211, you would have defined logic behavior as Boolean logic. So this is called behavior. So I just want to introduce these terms because I use these a lot. So logic behavior is essentially what the logic is doing functionally. And then you also would take those Boolean logic and you would translate them into gate designs. Sometimes these are called net lists or schematics, but this is called a structure. This is structure. So there's behavior and there's structure. So we're using a language that can define both behavior and structure. Behavior is essentially a truth table, right, or a state machine. And structure is when you define a schematic as a text file. So you say this component, I'm going to instance this component, I'm going to instance this component, I'm going to connect them together with wires. That's structure. So you did this in 211. You just sort of did a little bit, informally, and I assume you guys did it with paper and pencil, or you might have used Logisim. But either way, you had this notion of behavior versus structure, and you had a notion of synthesis, logic synthesis, which is when you have behavior and you compile it into structure, right? So this is a compilation process, much different than software. In software, you have a high-level program that's kind of converted down, lowered down into assembly instructions, assembly code instructions. Whereas in this class, we're taking behavior, which is not really a program. It's just kind of essentially what it amounts to Boolean logic. And it gets lowered down into gates and wires, right? So this is the schematic. So we go from behavior to structure, and the process is called synthesis, although sometimes I call it compilation, but it's more accurate to call it logic synthesis. And then in 211, you probably also looked at logic minimization, where you could take a complex Boolean logic expression and you can minimize it either through just Boolean logic or through Karnaugh maps or Quine-McCluskey or various types of minimization techniques to simplify it. And this is called mapping. This is basically where you're taking these gates and you look at this and you say, well, that's more gates than we need. Or maybe these gates are too big. These gates have too many inputs, and the ones I physically have on my chip are smaller than this. So you're taking this and you're mapping it down into another equivalent representation or another equivalent design. That's called mapping. So you're going to see this in those tools, in the Quartus tools. They have synthesis and then they have mapping, right? And then there's a process called place and route, which is where you take these virtual gates and you decide where exactly on the FPGA you want to allocate those, right? So this is equivalent to taking that gate level design and putting it on the breadboard, basically mapping each one of those gates into one of the slots on the 7400 series TTL logic chips, and then connecting the wires together. That's like routing. So this is the place and route. This is where you go into a physical design, right? You go from a logical design into a physical design, right? So in this class, we're going to be doing all of that, same process, except we're going to be doing it with CAD tools instead, which allows us to do it with much larger scale designs than you'd be able to do with this paper and pencil based approach. So just to give you an idea, like this is actually kind of obsolete now, but like a modern CPU, I calculated a few years ago, would take like 8 million breadboards, if you tried to build a modern CPU with the 211 style TTL chips and breadboards. Okay, so just to show this yet another way, so in this class we're going to introduce the FPGAs. Of course, you guys have used them in 3.13 already, but we're going to be deploying designs on these boards on the FPGA. And now you might say, well, this is kind of lame. I mean, why can't we just build a real chip? Like, why can't we tape out a chip? It's the same process. It's not the same process, but it's very similar. If you were going to tape out a same chip, an ASIC, an application-specific integrated circuit, you would follow essentially the same process. You'd start with the high-level code, the HDL code, hardware description code, and then you would synthesize it down and then eventually get it into a physical representation. In this class, the physical representation is a bit stream, which is used to program the FPGA. Whereas if you're doing design for manufacturing, the bit stream would be polygons, would be mask layers that you would send off to Taiwan, and they would fabricate your chip, and then they'd send back your chips. A very similar process. If you can do this, it's very easy to migrate this over into an ASIC type design flow. We don't make ASICs because it takes a long time to get them fabricated. We can't actually tape them out inside of a single semester. The FPGAs allow us to get instant gratification because we can design the logic and we can instantly realize it right on the FPGA. The FPGA allows us to conjure up a circuit not instantly. It takes like 20 seconds to program the FPGA, but we get a physical working chip without having to go through the ion deposition with vaporized arsenic, which is nasty. Okay, and then the hardware description language, as I mentioned, is a high-level language, and you just have to learn it. Unfortunately, you have to learn the syntax and the semantics. Now, you might say, wait a minute. Why would you use a language to design a circuit? That's stupid. Circuits are drawn in a schematic. Every circuit board is a schematic. It's not. You can't design a circuit board like this, right? Why would you design a gate level circuit like that? That's dumb. That's just the way it's done. That's the way. We used to use a schematic capture tool in this class years ago called HDL Advantage from Mentor Graphics, where you would draw the design. I think Quartus actually has this functionality built in somewhere, where you can draw it in a schematic, and then that schematic automatically gets converted into this textual format. But we don't do that because companies don't use those tools. If you go to work in industry, they write HDL. So that was one of the issues, and we learned that the hard way. It wasn't, we taught it this way, and then I started working with Convey Computer and Texas Instruments, and they're like, you guys no, we just write this stuff in a text editor. We don't use the schematic capture tools. Okay, right. Okay, and then FPGAs, just so I'm sure you guys know this already from 3.13, but an FPGA is a programmable logic circuit, and it's you power it up and it's a paperweight. It literally has no function, no benefit, no purpose, nothing. It does nothing when you power it up until you send it a bit stream through the JTAG port, and then you send in one bit at a time, and those bits are programming LUTs, lookup tables. Each lookup table is a logic gate, which is basically a truth table for each logic gate. And they have switch boxes that allow you to make arbitrary connections between the inputs and outputs of those LUTs through a programmable switch matrix fabric, right? And they do it literally like they had telephones back in 1910, where the operator would take the wire and connect it from one phone to another. That's literally what's going on, but it's happening inside the chip. So they literally have an old-timey telephone bank where you can make connections between these routing tracks on the chip, and that allows you to make arbitrary topologies, arbitrary connection patterns between the gates, right? And so there's two phases. You first program the LUTs, and then you program the switch boxes to create the connections. And once you do that, the logic that you design, the hardware you designed, it turns into a physical thing. It turns into a physical actualized circuit that you then can interact with. You can have it actually turn into a CPU. Now you might ask, well, wait a minute, if you can do that, then why would anybody make a chip? Why wouldn't everyone just use FPGAs for everything? Why isn't CPUs and GPUs built on top of FPGAs? You could do that. The problem, though, is that there is a drawback of an FPGA as compared to building a chip. An FPGA has 10 times less gates than an ASIC does, and it has 1/10 the clock speed, right? So you could build a GPU on an FPGA. In fact, if we had a follow-up, if we had a second class to this one, that's exactly what I would do. I would so totally build a GPU in the 611 part 2, right? You can build a GPU on an FPGA. It just would be only 1/10 the size and 1/10 the clock rate of an actual GPU. That's the problem. And why is that? Well, it's not because the chip is smaller. It's because that the logic density you sacrifice the logic density because of those switch boxes and the LUTs. Making a LUT is bigger than making an actual transistorized gate, right? Because a LUT is a little RAM, right? And that's actually less efficient than just wiring up a CMOS gate. Likewise, the switch boxes require, because the connections are programmable as opposed to just wires that you literally just trace out on a silicon wafer, they're going to be spaced out bigger, so less dense. So you sacrifice density. And then, of course, the clock rate is also tied to that density. The lower the density is, the farther apart the gates are, the lower the clock is, because you have more capacitance and resistance on those wires. That's basically it. Okay, so this is the CPU design. You might remember from 212, depending on who taught your 212 course. So this is shown as a schematic. So this is shown as a schematic when you took 212. And now we're going to be redesigning this in Verilog. So in this class, I give you the schematics, and you just, basically your goal is to just translate schematics into Verilog, right? That's, in a nutshell, what the labs are about, okay? All right, so one reasonable question that people ask about this class is, why do we need to learn hardware design? Because are there a lot of jobs in hardware design? Well, there didn't used to be a lot of jobs in hardware design, because if you needed a faster or more efficient, processor, you just wait and buy the next one, because you had Moore's law. Every 2 years or so, your CPU would be twice as fast as the previous generation. That's not true anymore. And so nowadays, there's a lot more hardware design because CPUs haven't gotten any faster in like 20 years. And I mean, of course, that's a kind of a secret. Not many people know that. But I literally have CPUs in my house that are 20 years old, and there's no discernible difference in their performance than a new one. They're no faster. And people don't even use CPUs for any heavy lifting anymore. It's GPUs. Like, all the neural networking stuff is GPUs. No one actually runs any expensive, large workloads on a CPU. Computer games mostly are on the GPU, right? So CPUs have been stalled for decades. They reached a fundamental limit on how fast you can make them. So now, anytime you want to get some kind of a new capability In fact, it's always fun to go back and look at. Every time there's this new revolutionary capability that comes out, a large part of that is because of the performance that is related to designing custom hardware for that capability. Now, I'm not trying to say that there's no algorithmic, innovations here at all. But like, for example, when the Tesla came out with the self-driving car, that wasn't, the algorithms that the Tesla uses to drive were around for decades. There was no innovation necessarily in the self-driving software. This was all hardware. This became possible once you had chips that could process frames at 30 frames per second from the cameras, right? Because before then they couldn't achieve that level of performance. So, and Tesla, of course, is like there's a lot of custom processors in there. And then, like if you look at when 4K video came out on phones, that was a custom, that's all done in hardware, customized hardware. In other words, the CPU that's in your phone is an ARM CPU. It doesn't do any 4K encoding or decoding. That's in a coprocessor, or an accelerator, or a domain-specific processor. That's in custom logic. Same thing with Face ID, animojis, computational photography, augmented reality. Basically anything that has to read input from a camera and process camera frames in real time cannot be done on a CPU. Because if it couldn't have been done 20 years ago on a CPU, it can't be done now on a CPU. So there's a lot of jobs in designing customized hardware for this stuff. And you can see that, like if you look at the floor plan of the Apple chips, the CPU, which I highlighted in white, as you know, that they use ARM CPUs on Apple chips, but they're basically not used for anything. They kind of just are orchestrators for the system. All of the workload is processed by a bunch of different specialized processors that are located elsewhere on the same die. And so you can see that generally only about 12% of the chip on an Apple chip is general purpose CPUs, ARM CPUs running Linux and iOS, or actually I should say BSD and iOS. Everything else is all of the other heavy lifting is done by specialized processors. And by the way, all of those specialized processors are all trade secrets. So there's a lot, you can learn a lot about how an ARM CPU works in the instruction set. You won't learn anything about any of this other stuff because this is generally all secret. Even to this day, the GPU on the Raspberry Pi 1 does not have an open architecture, open instruction set. You can't use GPGPU on even the original Raspberry Pi. People have been trying to reverse engineer that for 15 years or so. All of that hardware stuff tends to be big money and highly secretive. Same thing for CPUs. This is a little bit out of date, but you can see this is the Westmere processor from 2010. The CPUs comprise 72% of the die. Intel is really good about releasing the die pictures too. The Apple is not. Those Apple ones were taken by hackers, but these ones are released by Intel and they annotate what's going on. 72% of the chip was processors in 2010, then in 2013 it was 47%, and then in 2015 it was 20%. And you can see what's going on here. Over half the chip, even on a general purpose CPU, is graphics processing and specialized I/O and all that other kind of stuff. CPUs are just shrinking, shrinking, shrinking. Yes?
So the only really difference with older and newer processors is the fact that the new processors have more for the threads than the older.
Well, so they haven't even been growing. I used to have a chart of that too. I got rid of it because I got tired of updating it. But the number of cores is growing very slowly. According to Moore's law, the number of cores should be doubling every 2 years, right? Yeah. But I had a 4-core processor back in 2005. You know what I mean? Like, clearly has not been doubling every 2 years. Some of the recent CPUs have like 20 cores, like the desktop CPUs. But even then, some of them are performance cores and other ones are efficiency cores, and they have to make trade-offs there. But they're not scale. My point is that they're not. If you look at a CPU core, they're not scaling up the size of the CPU core. It's basically staying the same size, but the graphics processors are scaling up. All the special hardware stuff, they're able to scale that up. So if you look at the relative area on the chip of the CPUs versus the specialized hardware, the CPUs are shrinking, right, on a relative to the other stuff on there. Yes? Did you have a question?
I was gonna ask about the processor graphics and wondering if that was like assisting in the GPU's work.
Yeah, the irony is that not a lot of people use the graphics processor on Intel CPUs, but they still invest a lot of space for that, even though it's usually dark silicon, unless you use the integrate. My laptop is using it right now, but like if you have a desktop processor and you want to play a game, you can't use that. You can't use that.
Is that because you can't afford a GPU or
Yeah.
just standard?
Basically, yeah. And you can see they're also dedicating more and more logic to memory controllers. But my point is that this is all active work. Every time they come out with a new CPU, there's a bunch of hardware design that has to be done that has never been done before because they're innovating. They're innovating in these specialized processors much more than they are in the regular CPUs. Yes?
This also causes CPU to generate more heat.
Yeah, and they have to. There's this dark silicon problem where if you use everything on here, it'll exceed its thermal envelope. So of course, it has to manage clock speed and gating and that kind of stuff. Yeah, you can't even use everything at 100%. So yeah, and that's another important fact. When you're doing hardware design, often you're doing design specifically for energy efficiency. Okay, so yeah, my point is, yeah, there's not a ton of jobs still compared to software jobs, but there's an increasing number of people doing hardware design. That's why every new phone has basically a whole new chip with different processors on it. So in this course, I already talked about this. The first 2/3 of the class come off as a vocational school class a little bit because we just teach tools. And then the last third is more conceptual, more university-like. But the goal here is to give you an opportunity to design a CPU from scratch and get used to using the tools, the crappy tools, but still that's how the CAD tools are. And as I mentioned, we use the FPGA because we don't have time to tape out. Okay, so I want to start with assembly language because this is all review for you guys, but I'll go through this quickly. So people always ask me, why are we teaching assembly language in this class and in 212, right? Because nobody writes code in assembly language. There's not a job on earth where they write code in assembly language because compilers are really good, right? In fact, when I used to teach 212 back in the old days, mid-2000s, I used to have an extra credit lab where you had to write some inline assembly language in order to use the Intel SSE instructions. Those are the special multimedia vector instructions, SIMD instructions. Because it used to be 20 years ago, compilers would not generate code for those. Like, you couldn't write a for loop and have the compiler vectorize that for loop. In other words, turn it into, instead of scalar operations, vector operations, and map those into the Intel SSE instructions. Because Intel has 256-bit and 512-bit vector instructions, right? The compiler just didn't know how to do that. But nowadays it does. It's incredible. You compile something with GCC or Clang, and if you put a loop in there with any kind of arithmetic, and then you look at the assembly, you'll see a bunch of XMM registers in there. Those are the vector instructions. So you don't really have to do inline assembly or even intrinsics much anymore. So why are we teaching assembly then? Why? It's because it's also very painful, because this type of assembly that we're learning in this class is called RISC assembly, was not even meant for a human to write. It was deliberately made to be agonizingly painful for a human because RISC instructions are very simple, meaning that you have to write a lot of them, right? You have to write a whole lot of instructions to perform a very simple operation. And they were designed that specifically to make it easier for a compiler to generate them, but yet harder for a human to generate them, right? So when you're writing this assembly code by hand, it's painful, and it's painful literally by design. It's supposed to be painful. However, the reason why we teach it is because there is no way you can design a CPU without understanding how assembly language works, because the purpose of a CPU is just to execute assembly language, right? So in other words, you can't design the microarchitecture, which is what's under the hood, without understanding what the actual program model is that is designed to run on that architecture, right? So in order to design the circuits that fetch and execute instructions, you have to understand how those instructions work and what they do, what their behavior is. So as a result of that, we have to write some simple codes in this class as a way to test our CPU. And so in order to write a test bench, you got to understand the assembly language. So I don't go crazy with it. And if we want to do anything really complicated, you can always use a compiler to generate the RISC-V instructions. But you can't really do that until you're very confident your CPU is working. And before you get to that point, you're probably going to have to write some snippets of code yourself, right, to test it with. So that's why we teach that. It's not to torture you. It's just a part of the process for designing the hardware. Okay. All right. So the instruction set architecture is the kind of the native language of the CPU. It's the dialect. It's the native instructions that are executed by the CPU. And the microarchitecture is the underlying hardware. And the hardware operates, so the instructions are basically atomic, right? Meaning that one instruction is the smallest amount of work that software can be decomposed into, right? So, nothing can, get in, like an instruction is the fundamental unit of work. Inside the microarchitecture, the fundamental unit of work is called a data path. It's essentially a register connected to logic that feeds into another register. And inside of one clock cycle, that data path is executed. You have an update on the register value, the Q output of the register, which then propagates through logic and then enters the D input on another register. And at the end of that clock cycle, that value gets latched in, right? Gets clocked in, right? And so here we talk about instructions, and here we talk about data path operations, right? What happens inside of each clock cycle, essentially, right? Okay, so instruction set architecture is, there's different ISAs. There's obviously GPUs have one, Intel CPUs have one, it's x86 or IA64. ARM processors have one, RISC-V processors have one. In this class, we're going to learn the RISC-V just because it's become, it's because it's an open ISA. We used to teach MIPS, which for many years that was technically, we shouldn't have been doing that because MIPS, you're not allowed to build a MIPS processor without a license. But now MIPS is open. But before that happened, RISC-V came around, so we started using RISC-V. The other reason we're using RISC-V too, by the way, is that there's some stuff in MIPS that just doesn't make sense. There's some really bad decisions in RISC-V, one of which is the destination register in a MIPS instruction is in a different bit field depending on which instruction it is. So if you're doing an I-type instruction, it's the RT field. If you're an R-type instruction, it's the RD field. And that necessitated hardware, kind of redundant hardware. You had to put hardware in to select what the register that you wanted to write in the instruction was. That was stupid. Like, why did they do that? I mean, they should have, if they would have just had one consistent field that was always the destination register address, you just draw the wires directly there, and you don't need extra hardware and extra multiplexing in there. So there's a lot of things like that in MIPS that they fixed in RISC-V. And by the way, it was the same guys that designed both. They designed MIPS back at Berkeley in the early 80s, and then they capitalized on it by, they commercialized it, they made a bunch of money, and then of course it became, proprietary. And then after 30 years, they decided that they were going to do it again, but this time make it open. So that's kind of the history of RISC-V. But luckily, they're pretty similar. So let me skip that. I think you guys remember that stuff. Okay, so RISC-V is similar to MIPS. I mentioned some of this stuff. Yeah, so the RD field is consistent. Shifts are variable by default instead of MIPS had this weird thing too, where MIPS was the only instruction set I've ever seen that requires you to generate an exception on an arithmetic overflow. No other architecture does that. And so you might say, well, who cares? How does that affect us? Well, because there was an add instruction and then there was an add unsigned instruction. And basically you had to always use the add unsigned instruction and you had to implement both, but the one that you would use generally was the add unsigned. And everyone was like, why do we need add unsigned? That doesn't make any sense. The add hardware does the same thing whether it's signed or unsigned. It's the same exact hardware. The hardware doesn't care if it's signed or unsigned. Yes, but the CPU does, because if you get an overflow with the signed add, you're supposed to trap and go into an exception handler, right? In other words, segfault, essentially, in Linux. Stupid, like no one does that. No other processor does that. Makes no sense. That stuff should be handled by the software, not by the hardware. And then, you know, MIPS had like weird things, like they had jumps with link and jumps without link, and why not just link? Well, you can always link, and if you don't want to link, you just use register 0 as your link register, and then you're good. So that's that's the philosophy of RISC-V. So what ends up happening is that the RISC-V version of our CPU is a lot simpler than the MIPS version. So it actually helps you guys out. Your predecessors, when they did the MIPS version of this course, they had to write a lot more lines of code. RISC-V has some of the other, what I consider annoyances. So one of the things that RISC-V and MIPS both lack that other architectures do is an index register. What that means is that in your code, if you have an array, and you want to walk through the array, right? In C, you use an index for that, right? So you'll say, like, say, foo bracket I bracket, right? The problem is that there's no hardware support for that in MIPS or RISC-V. There's no index register. There's no way to specify an index of any kind, right? So that has to all be done in software, meaning that basically every time you access an array, you have to recalculate the effective address by having add instructions in there that add and multiply the index and put that onto a base address for your array, right? Now, you might say, well, I mean, aren't you kind of like splitting hairs? Like, who cares? That means for you guys to write code, you have to write a lot of instructions to walk through an array, a lot. And it introduces a lot of opportunities for bugs, right? All of that address calculation you have to do. That upsets me greatly. I wish they had an index register like the TI DSP architecture has and other architectures. I think even the IBM mainframe had an index register from the 1960s. Why they don't have it in here baffles me. But you'll learn more about this as we write code. Yes?
Was the reason why you had to calculate finding the index is because it was trying to calculate where to find it in the memory? Yeah,
so the idea is in your code, you have an index that's a variable. Your index is usually I, right? So you say for I equals 0, I less than 10, I plus plus, right? And then you use I as the index. I is a variable, right? So what that means is that you have to take the value of I and you have to add it. You have to use I to calculate the address of the value in the array that you want to access, right? That's something, in my opinion, that should be done in the hardware, not in the software, right? But yet you have to do it in the software with both MIPS and RISC-V. So that's kind of, and also they don't there's no auto increment for base. Typically if you're walking through an array, it would also be nice if there was hardware support to automatically increment the address, right? Like as opposed to you having to say add immediate, register 2, 4, you know, should be automatic, right? But they don't have that either. And then they do stuff like when you have a store instruction, they reverse the operand. So like typically the output is the first thing, right? So if you say add register 1, 2, 3, it puts the result in register 1, right? Right? That's meant to, the reason they do that is because it's meant to look like a left-hand side, like a left-hand and L value. Like so if you say in C, if you say A equals B plus C, A is the destination, it's on the left. So they do that in the instructions too, but for stores, it's the opposite. They put the store, you store to the right operand. So stuff like that. But anyway, those are just some annoying things that they didn't fix. I wish they had. And okay, so I mentioned too, this is what I was talking about earlier. A RISC instruction set is made to be is made to basically, it makes a trade-off. The trade-off is we're going to have a very few number of instructions. So we don't have to implement a lot of instructions. That's great for the hardware designer. It's very bad for the programmer because that means that the program will have a very big instruction count associated with it, right? But that's okay because the instructions, because there's so few instructions and they're so simple, we can make them really, really fast. So that's okay that we have a lot of instructions, but for someone writing it by hand, that's kind of an issue. So obviously with RISC leans very heavily on the compiler. Okay, and you guys remember the registers? There's 32 registers, right, in MIPS, 32 general purpose registers. So they're named differently though. In MIPS, they're like $0 through $31, and sometimes you can use there's like special symbolic values like S0 through S7. RISC-V changes that a bit. They don't use a $, they use X. But some of the other symbolic values are the same, except they have different numbers. Like they have S0 through S11, T0 through T6, A0 through A7. And those just map to, like register numbers. Now, we're going to use we have a simulator called RARS. You guys might have used Mars. Actually, you don't use Mars. Use Mars. I know that Punyan is using SPIM, or one of the XSPIM or something, which is wild to me because I used to use SPIM when I was a kid. I can't believe he went back to SPIM. SPIM is MIPS backwards, but that is such an old tool that's like a blast from the past. I guess they updated it though, but yeah, so Punyan was using SPIM. We use Mars. I like Mars because it's a really nice Java app and it's platform dependent, works on any machine, just run it. And it has an editor and a simulator are integrated together. So SPIM doesn't have that. SPIM is just a simulator. You write your code in a separate text file and then you run it through SPIM. Whereas Mars has a kind of just two sides of the same window. They have a text editor and the simulator, which is kind of cool. We use one in this class called RARS. RARS is obviously a variation of Mars that's for RISC-V. And we actually have a specialized version of it specifically for this class because in this class we have these special coprocessor registers that we use in order to send data out to the hex displays on the FPGA boards and to read the switch values. And so our version of RARS incorporates these special coprocessors that aren't in the normal RARS because they're not a part of the official RISC-V spec. It's something that we did for this class. Okay, let's see. Register 0 is always 0. You can write to register 0, but your writes are not actually committed to register 0. They don't change the value of register 0. So if you read from register 0, you always get 0, and if you write to it, it doesn't have any effect. And that's actually useful, like I mentioned the link register. If you don't want to write a link register, a return address from a function call, you can use register 0 for stuff like that. Okay. And then there's immediate instructions where, so MIPS and RISC-V are both what are called 3-address architectures, meaning that the R-type instructions have 3 addresses, 2 operands, 2 inputs, and 1 output. That's actually different from Intel. Intel assembly is a 2-address architecture. You give it 2 operands, but then the first of those 2 operands doubles as the destination, as the output, right? So you'll say, like in Intel, you'll say add A, B. You add the contents of A and B, and you put the result into A. RISC-V in MIPS are 3-address. Or you can have these immediate instructions where you can put a constant in there instead of the second input register. Okay? All right, so let's see. Actually, I think I might just stop there a little bit early. And I'll finish up the assembly language stuff on Monday, and we'll make the first assignment. So the first assignment is just writing some assembly code just to refresh your memory. But we will use that assembly code for a test program for your processor, right? So you get to reuse it. Okay? Okay, thank you.